Okay, hi everyone. Welcome to Experimental Methods Part 2, ANOVA. So last week we narrowed down our decision tree to scenarios in which we have a continuous dependent variable and categorical independent variable. And traditionally those are the experimental methods. And then last week we narrowed that down even further to scenarios in which you have two groups that you're comparing. So this week we're going to stick to the experimental methods, but we're going to look the other way and talk about the scenario in which you have three or more groups. That's this group over here, a family of tests called the ANOVA or F-test. And the good news is the basic principles are the same between the ANOVA and the T, except that the ANOVA can be used for multiple groups. So the obvious question here is why we need a whole other test for a scenario in which we have more than two groups. Why can't we just do a t-test for every combination? Like if we have three groups, why can't we just do three t's, comparing groups 1 and 2, 2 and 3, and 1 and 3? Well, the answer is what's called family-wise error rate. That means that the more tests you do on a single set of data, your type 1 error rate actually accumulates. In fact, the error accumulates in a predictable way, and we can actually calculate it using this formula here. The family-wise error rate is 1 minus the alpha to the exponent of the number of tests. Here, C equals the number of tests. So if we set the alpha at 0.05 for each of those three t-tests we talked about a second ago, we'd have a family-wise error rate of 0.14 or 14%. So our chances of falsely rejecting the null hypothesis have nearly tripled, and that's not okay. So what we need is called an omnibus test, a test that will tell us whether there are any differences in any of our pairs with just one test. The ANOVA. What the ANOVA does is tell us exactly that there's a significant difference somewhere in this data. It tells us that at least one of our means is likely to have come from a different population than our other means. In other words,
one of these things is not like the others. Which one is different? Do you know? Tell me which thing is not like the others, and I'll tell you if it is so.
So in ANOVA, the null hypothesis would be saying that all of our groups come from the same population. The alternative hypotheses are essentially going to be saying that there's another population involved somewhere, but we don't know where exactly. So we have one null hypothesis and then a bunch of alternative hypotheses, all of which come together to basically say one of these things is not like the others. This is how you'd write that up symbolically for a situation with three groups. There's one null hypothesis that we're going to try and disprove, but then a bunch of alternative hypotheses. They could all be different from each other, or mu1 could be different, but mu2 and 3 the same, or 1 and 2 could be the same and 3 different, or 1 and 3 could be the same and 2 different. Really, again, all the ANOVA does is tell us that the first null hypothesis, or the one null hypothesis is false. It won't ever tell us which of the alternative hypotheses is true. Again, all it does is say one of these things is not like the others. Also, of course, if you have more than three groups, then you're going to have even more potential alternative hypotheses, and the null hypothesis will still just be that all those means are the same. Now, the way the ANOVA determines that one of these things is not like the others is looking at two different ways that data can be variable. The first way data can be variable is within group variability. Within each of our groups, if we've assembled them properly and they're truly independent, any differences should be essentially random. The first student happens to be great at this task. The second to last student didn't eat breakfast. Someone accidentally picked the wrong answer on a Scantron sheet. Whatever. Any random reason that it could affect student scores will contribute to the within group variability. You could think of it as sort of like a people are different, surprise kind of variability. The other way data can be variable is between groups. Individuals between groups can also vary randomly. It's just as likely that someone in group 2 skipped breakfast as it is that someone in group 1 skipped breakfast. So when we look at between group variability, some of it is also randomness. But between groups, there's also a systematic difference, and that's going to be our manipulation or whatever we're comparing groups based on. So we expect some of the variability between groups to be systematic. So looking at it another way, our within groups variability is random. Our between groups variability is random and also systematic. There's a little bit of systematic in there ideally. So if we divide our between groups variability by our within group variability, then what we're really doing is dividing the systematic plus random variability by random only variability. If the null hypothesis were true, then we'd actually expect no systematic difference because they would all be from the same population. So we would expect the systematic part to be 0. So it would be random variability over random variability, which would equal 1. So the basic logic of the ANOVA is that if we take all the between groups variability and divide it by the within group variability, if the null hypothesis is true and all our groups come from the same population and sampling distribution, then we'd expect that to equal 1. If it's higher than 1, though, that would indicate that there's something beyond randomness in that between variability. There's some systematic difference in our data between the groups. In other words, one of these things is not like the others. So as you can see for ANOVAs, we're almost literally putting the difference over the noise in the logic of the ANOVA. It's more like difference plus noise over noise, but fundamentally it's the same thing. It's actually only a slight variation on the test we did for t-tests, which was itself a slight variation on the test we did for Z. All statistics are secretly exactly the same, you guys. Now, once we have the difference over noise value, we would still have to associate with a probability so we can decide whether to reject the null hypothesis. We can't measure an F-test or an ANOVA on a t-distribution or a Z-distribution, though, because now we have multiple kinds of degrees of freedom to account for. When we talked about t, we talked about how the degrees of freedom were restricted based on the size of the sample. For analyses where we have more than 2 groups, they're restricted both based on the size of the sample and also based on the number of groups. So our distribution is going to fluctuate in a couple of ways. Fortunately, those ways are also predictable, and that's what gives us the F distribution. As you can see in this illustration, the curves fluctuate not just based on the overall n-1 degrees of freedom, that's D1 in the image here, but also the number of groups -1 degrees of freedom, and that's D2 here in the illustration. And as you can probably already tell from the illustration, this is where finding our location on the curve and determining the probability stops being really visually intuitive. It's still what we're doing, but the curves, as you can see, look very different than what they did before. And that's actually partially because F is actually the squared version of the t-distribution when there are only two groups, obviously. So actually the black curve in each of these illustrations is the exact same curve. In a situation where there are 2 groups, so df2 equals 1, and the n-1 sample size is 1, that's the black case in both of those scenarios. It's just that the F distribution is squared. It's that exact t-curve, but squared. So it doesn't have our lovely familiar normal curve to it, but it is a normal distribution. And it has to be squared in order to account for the situation where we have more than 2 groups. So it looks really, really different, but it is exactly the same thing. So if you're wondering now whether it sounds like we could actually do an F-test or an ANOVA on situations where we only had 2 groups too, like if it's possible to have an F distribution for a scenario where we only have 2 groups and it's the exact same as the t distribution, then why can't we do F-tests when we only have 2 groups? Why can't we just do F-tests all the time? And the answer is there's absolutely no reason. Anything you can do a t-test for, you can do an F-test for. In fact, the F you get is going to be the same as t squared. So if we did a t-test, we could find the F value just by squaring it. Similarly, we could find a t value from an F-test in a situation where we only had 2 groups by taking the square root. So again, the F distribution, it looks like a big conceptual leap here, but it's really the exact same thing. Now, one important thing to note here, though, is that because it is squared, it's the squared version of t, there are no negative values. All the extreme values are at one end. That'll be a big deal later when we go to make our decision because, as you can probably already see from this F distribution, there's only one tail to it. There's no such thing as a 2-tailed F-test. So then it's also probably no big surprise that the assumptions of the ANOVA are the exact same as the assumptions of the t because they're basically the same test. So we need normality, homogeneity of the variance, and independence of observations. And like with the t, we can work with the first 2 if there's problems with it, but the third one is a much bigger deal. So that's the basic logic, and that's going to be true for all the different versions of ANOVA. But the ANOVA, much like the t-test, is going to fluctuate a bit depending on the type of data we collect and whether our groups are related or not. So we're going to need to expand this tree to include a few more decisions here. I'm also just going to get rid of the t-test ones for simplicity. Okay, so we've expanded our ANOVA group here to cover a lot of ground. Our first question is the same as it was for t-tests. Are our groups related? Just like t-tests, we could say collect data from 3 completely separate groups, say a control group and 2 different types of treatment. Or we could collect related data, let's say pre-test, immediate post-test, and then another post-test 2 weeks later to see if they retain that information. And just like a t-test, we're going to use a different ANOVA in each of those situations. So going to the left, when we have unrelated groups, we have to make another decision, which is how many dependent variables we have. See, ANOVA is actually really convenient in that it's flexible enough that we can have not just multiple groups, but actually multiple dependent and independent variables. So let's say that I have an intervention, and I think that it'll impact both grades and emotional well-being. I can test both those dependent variables using one ANOVA. In particular, I'm going to use a kind of ANOVA called a multivariate ANOVA, or a MANOVA. We're not actually going to talk a lot about that because they're more complex than we have time to get into, but it's important to know that they exist. Okay, so then let's go back to where we only have one dependent variable, and then we just have to think about how many independent variables we have. Like with dependent variables, ANOVAs have the ability to look at differences not just within one set of groups, but within multiple sets of groups, and then the interactions between them. So if I'm interested in, say, whether an intervention works and whether it works the same for boys and girls, that would be 2 independent variables. One, which is just treatment versus control, and the other, which is boys versus girls. I'll talk more about all that later, but suffice it to say now that if I have multiple independent variables, I do what's called a factorial ANOVA. And if I only have one independent variable, you do a one-way ANOVA, or a univariate ANOVA. As a minor side note here, if you have multiple independent variables and multiple dependent variables, you still do a multivariate ANOVA. The dependent variables is the important thing there. Okay, so those are all the options if I have unrelated groups. What do I do if I have a related groups? So let's go all the way to the right-hand side now. And there, it doesn't matter if we have multiple dependent variables or independent variables, they all use the same procedure, and it's called a repeated measures ANOVA, or an RM ANOVA. And then sometimes I might have multiple independent variables, and some of them are related and some of them are unrelated. The classic example of this would be if I had an intervention, let's say on vocabulary, and I wanted to see what words kids learned over a year of the intervention. So I give them a pretest and a post-test. That would be a related independent variable. But I also think that boys and girls may respond differently to the intervention, so I want to compare them too. So there, I'm just adding on another independent variable. But this one is unrelated. Boys and girls aren't matched on anything, they just happen to be boys and girls. In that case, it's called a mixed study, but I actually use the same procedure statistically, the RM ANOVA. If I have any variables that are related, I have to use the repeated measures ANOVA. So those are the options, and let's go and start with the simplest version. And that's the scenario in which we have one dependent variable and one independent variable, and they're both unrelated. That is the one-way ANOVA. Now the sampling distribution for the ANOVA is actually pretty straightforwardly our original sampling distribution of means. So the shape is normal, the expected mean is the same as the population mean, and the standard deviation is going to be the population standard deviation over root n. You remember from a few minutes ago that what we want to do is put the between variability over the within variability. So that means that last point, the standard deviation, is all we're really going to care about for this kind of analysis. In fact, surprise twist, ANOVA actually stands for analysis of variance. All we care about is the variability, and specifically the variance. So what we need to do here is take the total standard error, which you remember is the standard deviation of the sampling distribution, and we're going to split it. We're going to divide the total standard error into the standard error within, which is called mean squared error, and then the between standard error, which is going to be called mean squared between. That's going to let us determine where our variability is coming from and if there's any differences somewhere in our data. Okay, so here, before we go any further, here's some important notation that we're going to be using. K is going to be the number of levels of a factor, so the number of treatment conditions. If I have 3 groups, then K equals 3. N, lowercase n, is the number of scores in each treatment. So if I have 10 people in each group, N would be 10. And big N is the number of scores in the entire study. So if I have 3 groups, so K equals 3, and 10 people in each group, so little n equals 10, then big N would equal 30. And then SS just means the sums of squares, and I'll explain what that is in a second. So what we do when we calculate the ANOVA, and just as a side note, you don't have to calculate it in your lab assignments, but it is something that I think is really helpful to go through the motions of to sort of understand where ANOVAs come from. And if you want to, you should absolutely practice this if you're confused about what the ANOVA is. So I will go through the calculations for this one. So the calculations to get the different types of standard error, which we're of course going to want to divide, are a little different than what we've been seeing before. So instead of a formula, it's really more like a procedure, although some of the steps of that procedure will have some formulas. But essentially what we're going to do is we're going to fill out this table. Our goal is to get over to that MS column because the MS error is going to be our error term and the MS between is going to be that between variability, and we're going to want to divide the between variability by the error variability to get F, and then we can look up F in an F table. So that's our goal. But in order to do that, we can't just do it right away. Especially that MS error term is a real tricky thing, so we have to do some fancy footwork to get around it. So what we do is we move back over to the left of the table. And so remember again that what we're doing is dividing by the total variability into two pieces. Our goal here is to divide MS error in between. So our first column, named source, is just labeling which row is going to have which type of variability in it. We're looking for between variability and then error variability. And then if you added those two together, that would equal the total variability. So the first thing we're going to calculate is the sum of squares, SS. And the good news is calculating SS is something you've already done. The sums of squares is just the sum of squared deviations from the mean. In other words, it's the thing that we've been doing as a first step towards calculating the standard deviation this entire time. Now the good thing about the sum of squares is that we can do it in different ways and then add and subtract pieces of it and around it. So the first sums of squares we calculate is the total sums of squares. And like I said, that's actually the same thing you've been doing this entire time. Note that here, that this is the total sums of squares. So you're taking the entire sample and subtracting the mean for the entire sample. So you're not doing it group by group. You're pretending it's all one group and calculating that total sums of squares. But depending on how many data points you have, that can actually be a lot of work and more work than is really necessary. So here's just a shortcut formula that you can use for sums of squares. In this one, first we square every point and then we add those up and then we subtract the total squares divided by n. This is honestly the exact same thing as above. It's just algebraically manipulated to be a little simpler. Again, because we don't have to do these, you may or may not find this helpful, but I thought it would be good to provide this option. Okay? And then, I made up a little example here for the shortcut just to clarify how the shortcut works. But this is all made up. You haven't missed an example or anything. And then the next step is to calculate the sums of squares between. And this one's not exactly what we've done before, but it's pretty closely related. So what we're going to do is subtract each group mean, that's the little x, from the overall mean, that's the big X bar, square that, multiply it by the sample size for that group, then do that for all the groups and add them up. Again, I put in a little fake example here to give you a sense of what we're doing, but it's just made up. You don't have to stress about that, really. So once we've calculated that, we pop whatever number we get up here into the SS between. And then we also put in the total one that we should have put in before that I forgot about. And then getting the sums of squares error is as simple as taking the sums of squares total minus the sums of squares between. Basically, to sum up, this error variance is a really tricky beast to calculate. So the most efficient way to do it is to calculate the other two and subtract them to get the sums of squared error. That's really the whole reason behind this setup, is to get to the subtraction piece. And then once we have that, we just put it in here. So then now that we have all the different kinds of sums of squares, the next step is to calculate the degrees of freedom. Degrees of freedom here are actually pretty easy to calculate. The total degrees of freedom is going to be the total n minus 1, so big N minus 1. So if we have 3 groups and 10 participants in each group, that's going to be 30 minus 1, or 29. The DF between is going to be the number of groups minus 1. So if we have 3 groups, it'll be 3 minus 1. And then our degrees of freedom error is, again, just going to be their degrees of freedom total minus our degrees of freedom between. So just like with sums of squares, the DF error is the one that's the pain in the butt, so we're going backwards to get it. And then once we have each of those, they just go in here. Now to get this MS column, it's actually pretty simple. We're going to take the sums of squares in each row and divide it by the degrees of freedom in each row. So we take the sums of squares between and divide it by the degrees of freedom between to get the mean squared between. and then the sums of squared error divided by the degrees of freedom error to get the mean squared error. You don't have to go through and get the total error. Like I said, we just needed that to get the stupid, you don't have to go through to get the mean squared total. Like I said, we just needed that to get the stupid error portions, which were a pain in the butt, but we don't actually need the mean squared total for anything. And then finally, we divide the mean squared between by the mean squared error, just like we said we were going to do. That'll give us the f. So once we make our calculations and get a value for f, we need to make a decision. Now this works basically the same way as t, but with a couple of important differences. You may remember when we moved from z tables to t tables, the big change was that we had to start accounting for degrees of freedom. Well, the same thing is true for ANOVA, but now we have to account for two different kinds of degrees of freedom, our between degrees of freedom and our error degrees of freedom. So because f needs to account for two kinds of degrees of freedom, we actually need whole separate tables for each level of alpha, just because of, how space works. So I'm going to upload a couple options to our content page, so make sure you're using the right one for the one you want. Once we have the table we want, we look for our between degrees of freedom, here called numerator degrees of freedom, and it's along the top. And then the error degrees of freedom, or denominator degrees of freedom here, which is down the rows. That'll give us a critical f value, which we use the same way we use the critical t. If our f value is larger than the critical f, we reject the null hypothesis. The other big difference from t is that because of the way the f distribution is shaped, as I mentioned before, there's no such thing as a two-tailed test. So we choose the table that corresponds to alpha equals 0.05 or whatever we want to set alpha at, and we don't have to worry about dividing the probabilities or anything weird like that. So let's work through an example. Let's say that we want to compare whether taking a research methods course is better online or face-to-face, or a hybrid version where some stuff is online and some stuff is face-to-face. So our research question is, which version is better for learning? We sample 9 students and randomly assign them to learn either online, face-to-face, or hybrid, and then we compare their final scores. Our null hypothesis is that there's no difference between our means. And then we actually have several alternative hypotheses, but we don't have to write them all out. We just write out the null hypothesis and know that there are then several options for the alternative hypotheses. Now I put the means and SDs for each group in here, but because we're analyzing the variance, we need the raw data in order to calculate the ANOVA. Here's our raw data. And here's a summary table that we're going to fill out. First things first, sums of squares. Okay, remember that shortcut formula we saw before? Let's use that. I'll let you guys work through the data here, but hopefully as you do, you get 900 like I did. Okay, so let's put that right in here. And then let's go towards calculating the sums of squares between. I showed you the individual group means before, and those are the little x's, but we need to go through and calculate the overall mean, or the grand mean, in order to get this type of sums of squares. That turns out to be 80, so then we can go ahead and do our calculations. Again, you guys should do this yourselves too, but I get 600 here. So let's put that right in here. And then you remember that the error sums of squares is the total minus between, so that of course ends up being 300. And then we can put that one in too. And then hopefully we all remember how to calculate the total degrees of freedom, which is just the big N minus 1, so that would be 9 minus 1. Otherwise known as 8. And then to get the degrees of freedom between, we take the k, or number of groups, minus 1. In this case we have 3 groups, so the k minus 1 is 2. See? 2. And then finally, to get the degrees of freedom error, it's the df total minus the degrees of freedom between. So that's simple enough. 6. Okay, great progress. Now we're ready to move on to the mean squared column, the MS column. The mean squared between is the sums of squares between divided by the degrees of freedom between. So that would be 600 divided by 2, or 300. And then we need the mean squared error, which is now really easy to get. We just need to take the sums of squared error and divide it by the degrees of freedom error, which is 300 divided by 6, or 50. Now we don't need total anymore, remember, so we're actually done already with the mean squared part. What we need to do now is calculate the f, which is as simple as taking the mean squared between and dividing it by the mean squared error, which is 6. Okay, great job, us. Now that we have that, though, we need to find out if it's statistically significant. We need to move on to the decision step. As usual, we're going to set alpha at 0.05. Now, there's no such thing as a two-tailed test for an f-test, so we're going to be looking for the f-table that corresponds to alpha equals 0.05. Okay, so first we look for our between degrees of freedom, which is called here the numerator degrees of freedom, and that's k minus 1, and it was 2, so we're going to look in the second column here. Our error degrees of freedom, or denominator degrees of freedom in this chart, was 6, so we can find that too, which leads us here. The critical value of f is 5.14. Our value of 6 is higher than that critical f, so we can go ahead and reject the null hypothesis. So the way that we would write that is f with our two sets of degrees of freedom in the parentheses, first the between degrees of freedom and then the error degrees of freedom, and then the f value, and then the p is less than statistic. But of course, in reality, in which computers exist, we'd adjust that slightly to include the exact p-value, which I went ahead and ran this data, and at p it was equal to 0.036. Okay, so great. We've rejected our null hypothesis. But remember, there are lots of alternative hypotheses, so all we really know now is...
One of these things is not like the others. Which one is different? Do you know? Tell me which thing is not like the others, and I'll tell you if it is so.
Yeah, that's right. We know that one thing is not like the others, but we don't know which one or whether it's more than one. So what we need to do is we need a follow-up to determine where that difference is. Which of these things is not like the others, so to speak. And the way we do that is through follow-up tests called post hoc tests. Post hoc means after, so it literally means the test you run after the ANOVA. There are a bunch of different kinds of post hoc tests you can do, but we're only going to talk about 3 of them, and they're relatively common in education research. You are, of course, encouraged to find out about the others as you're exploring options for your own research, and you may see different ones in different literature. The first one we'll talk about is the LSD test. LSD stands for least significant difference. It's also sometimes called a protected t-test, and that's because it is straight up doing t-tests for every comparison we want to do. We adjust the formula a tiny bit. Essentially, instead of the pooled variance, we're using the MS error here, and that's because we need to account for the error in all 3 groups, even though we're only directly comparing 2 groups right now. But essentially, it's a t-test. So why is it okay to do a t-test now when before we said it unacceptably inflated the alpha? Well, the reason is that doing that omnibus test first, the ANOVA, gives it some cover. It protects it. That's why it's called a protected t. And let me walk you through how that works. We talked about how the ANOVA has multiple alternative hypotheses. So here's a list of the null hypothesis and all the potential alternative hypotheses for a 3-group scenario. In the actual world, one of these things has to be accurate. These are all the potential options. Now, the first one is listed as the null hypothesis, but we've already rejected that based on our ANOVA. Now, we have a 5% chance of being wrong about that, of course, because alpha was set at 0.05. But at this point, if we're wrong, we're wrong. We've already made that error. So we have to progress as though we've correctly rejected it. We have to assume that we're right and that this option, this top listed option, is no longer one of the possible real-world scenarios of what's going on. The next 3 hypotheses imply a world in which one of the means is different from the other 2, but 2 of those means are the same. So for the first example, in the real world, it would be that means 2 and 3 are the same, and means 1 and 2 are different, and means 1 and 3 are different. So if we ran individual t-tests here, then there's only one of those tests where we could potentially make a type 1 error. That's comparing groups 2 and 3, because if you look over at our chart of error types, which I've replicated here, one of those 3 t-tests, 2 of them show a situation where the effect actually exists in the real world. Therefore, it's impossible to falsely reject the null hypothesis in those tests. The only test where we could, theoretically, make a type 1 error is for the one comparison in each of these 3 alternative hypotheses where the means are the same. Because we can only make that type 1 error in one of those tests, then we're not actually inflating our error. Our chances of making a type 1 error for all 3 of those tests is 0.05. Now, the final solution is the one where reality shows that all 3 groups are different from one another. And in that scenario, it's impossible to commit a type 1 error at all because in the actual situation, the effect exists. So anytime we reject that null hypothesis, we're going to be right. So essentially, the logic is that once the ANOVA has eliminated that first option, the full null hypothesis, the rest of all the other possible alternative hypotheses, if you do t-tests on them, you have a type 1 error rate of whatever you set your alpha at, which we usually set at 0.05, or it could be even lower. So we can feel comfortable using t-tests because we've eliminated the only version where we would be making multiple type 1 errors. A caveat to this, though, is that it only holds up when we're dealing with exactly 3 groups. So if you have more than that, you're going to need another option. Enter the Bonferroni post hoc. Bonferroni is also just a series of t-tests. It's literally the exact same formula as the LSD test. I mean, I literally just copied and pasted it. The only difference is that in order to account for inflating family-wise error rate, we make an adjustment at the decision step. Essentially, if our goal is to have a total family-wise error rate be 0.05, then we adjust our alpha, that's where we set our cutoff point, remember, that is 0.05. We adjust that to be lower. So specifically, we're going to divide alpha by the number of comparisons that we want to do. So if we wanted to do 3 comparisons, we divide the final alpha that we want by 3. So that would mean that we're now setting, in this case, an alpha of 0.017. If we wanted it to be 0.05, we would divide 0.05 by the number of comparisons we want to do, in this case 3, and that would give us a new alpha of 0.017. Then you'd go to your t-table after calculating each of those t's for each of those 3 tests. You'd use the column that's associated with your new alpha. In this case, 0.017, we'd want to divide that again by 2 to make it two-tailed, because for t-tests we can do that. So it would be around 0.008, so we'd be looking somewhere between here and here. The table doesn't have the exact value we need, so we'd actually need to move to a computer to get a more precise estimate. So if LSD and Bonferroni are both just running a bunch of t-tests, why would we choose to use one or the other? And the answer is it depends on what you're doing and why, and also like who you are as a person. So the LSD is more liberal, where Bonferroni is more conservative, which means that for LSD you have a greater chance of making a type 1 error. For Bonferroni, your chances of making a type 1 error are very low, but that does mean your chances for making a type 2 error are higher. LSD really hinges on this whole idea that the ANOVA is accurate, that you've successfully eliminated the one option that ruins this. If you've made a type 1 error at the ANOVA level, then your least significant difference test is screwed. Whereas for Bonferroni, because you're adding on that extra correction, even if your ANOVA is wrong, you're still reducing your chances of making a type 1 error. Similarly, LSD only works if you have fewer than 3 groups. And Bonferroni can be used for any number of groups, although the more groups you have, the lower and lower your cutoff for significance will be, to the point that it really stops being meaningful at some point. So although they can theoretically be used for many groups, once you get past 4 or 5 or so, it's really not helpful at all. And then some reviewers and editors don't really like or buy the logic that your alpha doesn't really increase with the LSD, so they may request additional corrections to your family-wise error rate. For Bonferroni, though, some editors and reviewers don't have any idea what you're talking about, so there's always something to think about. Okay, so those are the pros and cons of the LSD and Bonferroni tests. And what you may have noticed is that neither of them are really great when we start having a lot of groups. Once you get past a certain number of comparisons, it really stops being helpful. LSD because it no longer, the logic no longer holds up, and Bonferroni because you're dealing with alpha levels so small eventually that you can't in any practical way apply them. So in the scenario where you want to do a lot of different tests, you need one of the big gun post hocs, the most common of which is Tukey's. It's also sometimes called Tukey's HSD, which stands for honestly significant difference, Tukey's range test, or Tukey's method. And what it does is essentially, instead of using a t-test and a t-distribution, you use a q-test and a q-distribution. The q-distribution is very similar to t, but it allows for the comparison of multiple means at the same time. I'm not even going to show you the formula for q because it's a bit tricky, so we can just, find a computer and have them give it to us. But I did want to quickly show you a Q table. You can see it works like an F table where you have the number of means you're comparing along the top and then the error degrees of freedom along the rows. And that'll give you a critical Q number that you can then compare to the Q you calculate and see if it's different. Of course, in reality, since you guys aren't doing this by hand, you'll just look in SPSS and be like, yeah, that's lower than 0.05 and call it a day. And then one last thing about Tukey is that they're very conservative, especially when you have unequal sample sizes. So you're unlikely to make a type 1 error with Tukey, but you are more likely to make a type 2 error. So all these different post hocs, you may have already realized, are basically just ways of doing the same thing. Essentially, they're different ways of doing pairwise comparisons. So all we're really doing here is moving from
One of these things is not like the other.
to.
T for two, two for tea.
Now each of those ways of doing pairwise comparisons has their own pros and cons. And since they're all ways of doing pairwise comparisons, that means that once we've done the post hocs, we can use the same Cohen's d in order to calculate effect size. So that's one less thing to worry about. Okay, so that covers the one way. Let's move on a little bit to the factorial ANOVA. So the fun thing about the factorial ANOVA is that we have two independent variables, or more than two. We have multiple independent variables. The logic of the factorial ANOVA works roughly the same as the one-way ANOVA. In fact, it would no longer be a factorial ANOVA if we didn't have multiple independent variables. It would be exactly the same as the one-way. There would be no difference whatsoever, the same calculations and everything. But when you have multiple independent variables, what we're essentially doing is breaking down that between group variability even further. Essentially, instead of looking at just as between group variability, there's some systematic variance in here. What we're saying is that we're looking at the variability that's systematically related to one independent variable, the variability that's systematically related to the second independent variable, and the variability that's related to how the two work together systematically. This was our summary table for the one-way. We're going to take the exact same thing and then we're just going to add some rows so that we can break down that between variability into multiple chunks. Here we go. Now we can account for the between variability in three different ways. The variability that is systematically related to independent variable 1, the variability that's systematically related to independent variable 2, and the variability that is systematically related to how they work together. Now, I'm not actually going to go through and calculate these. It's more complicated than it's worth for what we want to do. But I will go through how we interpret this summary table once we have it filled out with data. And whatever computer program you use, if you do a factorial ANOVA, this is exactly what that table looks like. They'll throw out this exact summary table. I mean, it won't be green, but you know what I mean. So in order to figure out how to interpret the summary table, let's actually start with an example. So my step 1 question is, I have a vocabulary intervention targeted towards early elementary kids. I want to test whether it works in both JK and SK, but also whether it works differently in each grade. So in that case, I have two independent variables, each of which has two levels. I would call that a 2 by 2 ANOVA. I know one independent variable has two groups and a second independent variable has two groups. So I have two independent variables, each of which have two different levels. Now, if I had more than two independent variables, then I can have more than two independent variables per group. And we could call that adding levels or adding independent variables. And both of those would be covered under a factorial ANOVA. So say I want to test whether my treatment worked at JK, SK, and grade 1. In that case, I'd have a 2 by 3 ANOVA. Independent variable 1, treatment versus control, has two levels, and independent variable 2, grade, has three levels now. So if I had a third independent variable, say gender, then it would be 2 by 3 by 2. Treatment control is the first 2 level, grade is a 3 level, and then gender, which would also have 2 in this case. So this is just to say that these variations are possible. We're going to go back to the original version for our actual example. So back to our original setup, we have a 2 by 2 design. So I collect a sample of JKs and SKs, and each group gets randomly assigned to either treatment or control. And by that I mean the 97 JKs get randomly assigned. So there are half of them or 62 of them in treatment, and then 35 of them in control. Next, we set up our null hypothesis. In this case, because we have multiple independent variables, we're going to have multiple null hypotheses. The first two are pretty intuitive based on what we've been doing so far. The mu for treatment is equal to the mu for control. The mu for JK is equal to SK. The big difference here is this third one, and it's saying that the interaction between the two independent variables will be 0. In other words, that one independent variable won't behave differently depending on the other independent variable. As we go through and explain it, I think that'll make more sense. So here are the means and standard deviations for our groups. Of course, we need the raw data to get the summary table, same as we did with the one-way, because variance, the ANOVA is still doing an analysis of variance. That's what that means. But here you can see that the means and standard deviations of each possible combination, as well as the total, averaged across the other independent variable. So on the right-hand side, you have the average score for all JKs, regardless of whether they were in treatment or control, and then all SKs. Okay, so here's where we get to the good stuff. You enter your data into SPSS, and this is the summary table that comes out. As you can see, it's fundamentally the same as the one we had with the one-way. The big difference that you might notice, is that the sums of squares don't actually add up to the total sums of squares. That's because there's some overlap in the variance between the interaction term and the individual independent variable terms. We can't split those perfectly evenly the way we could when we only had one independent variable. We'll talk in a second about what that means for interpretation, but for now, just know that fundamentally this table is the one that we've worked out before, and we get the different mean squared numbers for between and error, and then we put each MS between over the MS error to get an F statistic. We could now go to an F table and look up the critical value, and then compare each of these to that critical F value in order to determine whether it's significant. But there's no reason to do that if we're not calculating by hand. So instead, let's just let SPSS spit out our exact probabilities for us. So here we can see the exact probability of getting these means if the null hypothesis were true. So we just have to look at them, and if they're low, and if those p-values are lower than 0.05, we can go ahead and reject the associated null hypothesis. But what does that mean when we have multiple variables? Well, these two are what are called main effects. They're the individual effects of our two independent variables. So let's start at the top. Our p-value for the main effect of treatment is lower than 0.05, so that would mean that we have a significant main effect of treatment. Okay, so what does that mean? Essentially, it means that there's a difference somewhere in our treatment and control groups on average. So completely ignoring the grade difference, if we averaged across grades, is there a difference between treatment and control? Our F-test says yes. Now that we have three groups here, if we had three groups here, we'd have to go ahead and do a post hoc to determine where in those groups the difference lies. But in this case, because we only have two groups, one of these things that is not like the other is actually super straightforward. We can just look at the means and say that the average treatment score is higher than the average control score. So let's move on to the next one. 0.607 is not lower than 0.05, so that would suggest that there's no main effect of grade. We can't reject that null hypothesis. We have to fail to reject it. So what does that mean? Well, it means essentially that there's no evidence that these means are different. There's no difference somewhere in these averages. So ignoring treatment and control, JK and SK, we have no evidence that they're not performing the same. We can't really say what they're doing, but we can't say that they're different. And then finally, our interaction term is lower than 0.05, so we can reject that null hypothesis and say that there's an interaction between treatment and grade. Now, what does that mean? Well, it means that one of these relationships is not like the others. So there's a difference somewhere in these four means, but specifically the relationship between one of the independent variables is different at one of the levels of the other independent variable. Or to put it another way, one of these differences is not like the other differences. To figure out where that difference is, the easiest thing to do is draw a figure with all these means and then see what the relationship looks like. So we designed a figure in which we have one independent variable along the x-axis and separate lines for the other independent variable. When we set it up this way, it's actually pretty clear to see that the JKs increase a lot from being in the treatment group, whereas the SK kids are pretty much the same in both groups. Now, what would happen if we switch the graph to have grade along the x-axis and treatment and control be along the different lines? You could do it, but it's not as clear as this one. And if you'd like, I'd encourage you to take the means and standard deviations and work it out the opposite way and see if it's as clear to you. So if you're wondering now how you're supposed to know which version of this graph is better for your data, well, you would go back to your research question. I'm not interested in the differences between grades. JKs knowing more or less vocab than SKs is not something I'm interested in and of itself. What I'm interested in is whether my intervention operates the same in both grades. So the intervention is the main thing I'm interested in, so it's the thing that goes on the x-axis. Okay, so now that this figure has given me some ideas, what do I do? All our ANOVA told us is that one of these relationships is different, and there are 4 options for relationships. Looking at this, I have a pretty strong guess that it's going to be that treatment versus control is different at each grade level. So I'm going to go ahead and test that, and I'm going to test it using the same post hocs I would have used for the one-way. In this case, because I'm only interested in the relationship between treatment and control at each grade level, I'm only doing 2 comparisons. Treatment versus control at JK for JK students and treatment versus control for senior kindergarten students. I can get away with an LSD in that case because I'm only doing 2 comparisons, so that's what I'm going to go ahead and do. So when we do that, what we see is it works out pretty much exactly as we thought. In JK, there's a significant effect of treatment, and in SK, there's no significant effect. For these post hocs, we only have to follow up with a p-value, but of course for our f-tests, we have to present the whole thing, and this is how we'd write that. Same principle as the one-way, but of course, this time we have more f's to report. And you have to report all of them, even the ones that are non-significant. Now going back to our summary table for a moment, do you remember when I said that one of the big differences here from the one-way was that the sums of squares didn't work out perfectly to the total because we can't perfectly split the interaction from the main effects? Well, that's not nothing. What that means is that if you have a significant interaction, as we do here, then you have to be very careful about interpreting your main effects because some of that variability overlaps. And we can see that exact issue in our data. We found a significant main effect of the intervention, but we also had a significant interaction. And when we explored our interaction term with post hocs, it turned out that our intervention really only impacted the JK group. But it impacted the JK group enough that the systematic variability overlapped with the main effect because the main effect is taking the average. So all we can do about that is be really careful in our interpretations. We wouldn't want to go ahead and say that this intervention works because we know it only really works with one grade level. We would probably feel comfortable saying that it worked with JKs, but we don't want to take the main effect, this intervention works, as being the truth. So that's the basic logic of how a factorial ANOVA works and how we interpret it. And most of these interpretations work no matter what kind of data you have or how your results turn out. With one big exception, and that is that with the interactions and how those interactions work with main effects. How interactions and main effects looks is going to be a little different based on your data, but there are some really common patterns, and this chart shows a lot of the different ways that data and main effects can interact. Here the study is how the amount of exercise you get and what time of day you get it influences your sleeping habits. You can see here how data looks different depending on the different effects. They've outlined each possibility or significant main effect and significant interaction combinations, and I encourage you guys to spend some time with these and really think about them, and then we'll discuss them more in the discussions. At the very least, try and figure out which one of these our example best matches. Okay, so that covers the factorial pretty well. We're not going to talk about multivariate because that's a little more complicated than we want to do in this kind of course. So let's shift all the way over to the right and look at the repeated measures ANOVA. That's over here. Now we actually use the repeated measures ANOVA when any of our independent variables are related. So it works for both a situation where you have a related independent variable with more than 2 groups, or we have multiple related independent variables, or we have some related independent variables and some unrelated independent variables. They all get covered by the repeated measures ANOVA. Now the good news here is that the logic of repeated measures ANOVA is again pretty much the same as the original one-way. The only real difference here is that within the variability there's another way that the variability can be systematic. That is, if these data points are the same people at different time points, then they vary not just randomly and not just by the growth between groups or over the group, they vary person to person, which is going to be systematic. In other words, all the error has this added element of this person-specific variability. So within each group and time point, there's within-group variability, same as before. And in each time point, there's systematic variability because of that shift in time. And within those, there's some variability of going from time 1 to time 2 that's not systematically associated with the time of testing, but is systematically associated with the person. So, for example, one person could be really great at this, and from time 1 to time 2, they're getting better based on the fact that the intervention works or whatever. but there's still some of that that is related to them as a person. So some of it is that the intervention works, and some of it is that they are a person and they're likely to perform consistently time to time. So to put it another way, what we're going to do is take out the variance that's systematic due to participants being the same or related in each group. That actually comes out of the error because it's systematic, but it's systematic in a way we don't care about. We already know that people are different. So what we're going to be doing is accounting for some of that error that was all getting tossed in the within participants error before. And that means that over on the right-hand side here, this part of the equation hasn't changed at all. We're still putting random plus systematic over random. It's just that now we have a stronger measure of that random variable because we can take out some of the variance that we know isn't actually random, but is due to the person. Now, if I were going to show you how to calculate this, which I won't, this is the summary table we would use. Let's say we were interested in student scores on a test at pre-test, mid-semester, and then at end of term. So we have one related independent variable, which is time of testing. Then we'd have to work out the sums of squares for the between variable, for the subject, and the total. And then the error is going to be the total minus the between and subject. So the only difference in calculations here from the one way is that the sums of squared error is going to be a little smaller than it otherwise would be because we're calculating this sums of squares subject and taking that out of it. We're subtracting both the between variability, which we were always subtracting before, and this new subject variability. The degrees of freedom and mean squared and all F's are all calculated the exact same way that they were before. The only difference is that now we're calculating this subject variability, which I'm not even going to show you how to do because you can just get it. And when I say get it, I actually don't mean this time, although I usually do. The SPSS just spits out the numbers for you. It actually doesn't give you that subject variability. And that's because the subject variability can't be turned into an F test. You can't calculate the F of subject variability because the mean squared error is not the correct denominator for that F test. So what it does is SPSS will just take out the subject related variability and not give it to you. It does it automatically. It happens behind the scenes. So we do not have to worry about it at all. What is going to come out on SPSS is going to be the exact same as the one way. The variance due to your between variable, the error, and the total, except the error is going to be smaller than you thought it would be. So a lot of times I find that education researchers, especially older ones, don't do a repeated measures ANOVA, like they try to avoid it. And I think part of it is the lingering hangover from how hard it used to be to calculate. So I recently did a review of the Canadian Journal of Education, and they have published 0 studies that use a repeated measures ANOVA since 2010. But they're super handy and they're easy to do on a computer. So let's go through a really fairly complicated repeated measures ANOVA. Or a situation where repeated measures ANOVA is necessary and helpful. So let's take the exact example we just used, a vocabulary intervention for JK and SK, but this time we give them both a pre-test and a post-test, so we can actually chart growth in vocabulary. The principles of these null hypothesis work here the same as they did for the factorial ANOVA, but this time we actually have 3 independent variables because we're adding this time one on, right? And so we have more null hypotheses because we have more main effects and more interactions that we need to account for. So here are the means and standard deviations that we get from this. The post-test ones are the exact same ones as we used in the last example. I've just added in these pre-test ones. So SPSS actually gives us 2 summary tables here. One for the only unrelated variables and one for all the related variables or interactions that include at least one related variable. So first let's look at the unrelated variables because they're basically the same as the ones we just saw for the factorial. The numbers themselves are a little different because this is accounting for the fact that we have another variable going on here, but it's averaging across the pre and post-test data. So we see the same thing, a significant effective treatment and a significant treatment by grade interaction. So now let's look at the related stuff. And we can see we have a significant effective time, that's pre-test to post-test, I just called it time to save space. So kids get better pre-test to post-test, that's good news. There's also, as you can see, many more interaction terms. That's because time can interact with each of the unrelated variables and all 3 of them can interact together. You can also see here that none of them are significant. And that's actually really bad news in this case. what that means is that although kids grow from pretest to post-test, that growth doesn't depend on being in the treatment group or either grade. And if I'm doing an intervention, I want it to be dependent on the treatment group. I want kids in the treatment group to grow more from pretest to post-test than they do if they're in the control group. So that means if that interaction is not significant, that means we're going to have to reevaluate our results from that unrelated, both the factorial ANOVA that we did before and the unrelated summary table. Because if we're seeing a difference between treatment and control, but that difference doesn't change over time, well, that really just makes it look like our whole effect is really just that. Through random happenstance, our JK treatment group happened to be really high at both time points. Basically, you can see with the arrows here, these kids seem to have randomly just had a really high vocabulary compared to all the other groups. And that messed up our whole test, both the factorial ANOVA we did originally and this and our interpretation of the unrelated effects, those between groups effects. So having the pretest and doing a repeated measures ANOVA here gave us information that otherwise we would have concluded that our intervention worked great for JK students. Now we see that actually we can't draw that conclusion. Now, if there had been a significant interaction, we would have done the same thing we did in the factorial ANOVA. The figures aren't as helpful when there are more than two independent variables, but we still would have drawn them and we would have seen what the interaction was saying and then run the post hocs to test those differences based on our research question. And one big caveat to this, though, is that repeated measures ANOVA can't do post hocs the way we've done them before for the related variables. So we can do LSD and Bonferroni and Tukey on the unrelated variables, like treatment and control, etc., the same way we did for the one-way and the factorial ANOVA. But the related variables, or the within subjects variables, just don't work that way. So if we have to run post hocs there, we have to do entirely separate t-tests and account for the family-wise error rate manually. And then the effect size, much like the f-tests, we will take from the post hocs, so that would be a D. Okay, that's ANOVAs. Whew, this was a long one, but you guys made it through, so congrats.